Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry Paper 3. In Unit 2, we are studying about polynuclear hydrocarbons. In Lecture 3, we will be studying about phenanthrene and its derivatives. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. The topics that will be covered in this session include structural elucidation of phenanthrene. We will study about what is the molecular formula of phenanthrene and how many rings are present in phenanthrene and whether they are connected through an angular fashion or a linear fashion we will study. We will also study about the position of double bonds and the application of Rice and Clare rule for the structure of phenanthrene. So, which ring is highly reactive, which ring is more stable, all those things we will study. Then we will study about the preparation of phenanthrene. The various methods we will study include preparation using Fittig reaction, Schar synthesis, Haworth method, Stobbe condensation. So, how benzene can be converted to phenanthrene we will be studying, and what is the Stobbe condensation, what are the reagent used in this reaction, all those things we will study. Then we will study about reactions of phenanthrene. What is the reduction reaction, halogenation reaction, oxidation reaction, and what are the different products that will be formed from phenanthrene, all those things we will study. Welcome to the next session. In this session, we will be looking at phenanthrene and its derivatives. Let us briefly take an overview of phenanthrene. Phenanthrene is having a molecular formula C14H10 and it is mainly occurring in coal tar. It is an example of angular polynuclear hydrocarbon. Angular polynuclear hydrocarbon is written as here. So, here we have benzene ring 1. So, we have 3 benzene rings. They are numbered as 1, 2, 3. So, they are connected in a angular fashion, and certain alkaloids like morphine and steroids like cholesterol have a very similar structure. So, if you look at the morphine structure, we can actually see the 3 rings 1, 2 and 3. These 3 rings are having a very similar to phenanthrene like structure, and if you look at cholesterol, here again we have rings 1, 2, 3. These 3 rings also have a structure which is very similar to phenanthrene. So, various alkaloids and steroids have a very similar structure to phenanthrene, or in other words we can say the angular arrangement of cyclic system is seen in these type of compounds. And when we look at the electrophilic substitution, the phenanthrene electrophilic substitution occurs in position 9 and position 10. So, this position 9 and position 10 are the 2 places where generally the electrophilic substitution occurs. Let us look into the structural elucidation of phenanthrene. Phenanthrene is having the molecular formula C14H10 and as we have seen it is having a angular structure, polynucleic nuclear structure. We have 3 rings 1, 2 and 3. Now we will find it out. How do we know exactly there are 3 rings and how they are actually connected? All those things we will study now in the structural elucidation part. So, the oxidation of phenanthrene using sodium dichromate in acetic acid actually produces 9,10 phenanthrene. So, as we mentioned earlier, this 9 and 10 position undergo reactions very readily. So, here it undergoes oxidation to give 9,10 phenanthroquinone. And when we do the oxidation using sodium dichromate and sulfuric acid, which is a much stronger oxidizing agent, we end up with a dicarboxylic acid, that is a 2,2'-diphenic acid. So, this X group, both the X groups are basically carboxylic acid groups, and this is how we actually can find out there are 3 ring structures are there. If you recall what we studied about naphthalene, naphthalene is having 2 benzene ring structures. So, when we oxidize naphthalene, we end up with phthalic acid as the derivative. So, if you look at the structure of naphthalene, we have 2 benzene rings connected to each other, and oxidation of this leads to the formation of phthalic acid. We have an acid group and another acid here. So from that the nitration and amination reaction, we found out there are 2 rings present in naphthalene. So similar to that, if we extend the same analogy here we can actually say there are 3 rings are supposed to be there, because oxidation of one of the ring leads to dicarboxylic acid. So if you look at the carboxylic acid in phthalic acid, these 2 are coming from one of the aromatic ring that is present in naphthalene. So similar to that, we can also assume that these 2 carboxylic acid are actually coming from one of the ring. And since there are 2 benzene rings attached by a carbon-carbon bond as shown here, so that means we can actually infer and say there are 3 rings are present in phenanthrene. And now the question is going to be whether these 3 are in a linear fashion or they are connected in the angular fashion. So that is the only thing we have to find out. But now that we know there are 3 rings are present, and we also know they are fused together. So this is the basic information we have right now when we talk about oxidation reactions. So we have to go further to find out whether this is a linear connection or angular connection. So that is the only thing we have to find out by other means, because we know there are 3 rings. One of the ring on oxidation gives dicarboxylic acid. So 2 carboxylic acid are obtained from one aromatic ring, and we already have 2 other aromatic rings. So total 3 rings are accounted for C14H10 molecular formula. Now we have to find out the position of the double bonds then, because from that we can actually deduce what is the actual structure. So similar to benzene, which is having a resonance energy 36 kilocalories per mole, the phenanthrene is having a resonance energy of 92 kilocalories per mole. So we can actually write various resonance structures for this particular compound. So we can, if you look at the various structures, in the structure 1 we have 1, 2. 2 rings are having 6 pi electrons and 1 ring is having 2 pi electrons only. So total we have 6 plus 6, 12 plus 2, 14 pi electrons are accounted for, but because this molecule has 14 pi electrons. So according to Huckel rule, if we substitute 4n plus 2 pi electrons rule for aromaticity, when n equal to 3, we have 4 into 3, 12 plus 2, 14. So we end up with the 14 pi electrons. So this system is an aromatic system. So it is also showing resonance, and various delocalization of the pi electron leads to different structures. So one of the structure has 6 pi electrons in 2 benzene rings, and another one having 2 electrons only, the third ring having only 2 electrons. We can also write different structures with 4 electrons each in 2 rings and 6 electrons in another only one of the ring. So like that we can actually draw various resonance structures for the phenanthrene molecule. In that case, if you look at most of the structures, this position 9 and 10 position, what we call this particular structure is having a double bond here. Again, in another structure we have a double bond here. We have another structure which is having a double bond here. We have another structure double bond here, and except only one of the structures. So that means 4 out of 5 structures we have a double bond in position 9 and 10. So this is one of the reason this position undergoes reaction very readily, and when we look at the Clark rule and Fry's rule, we will understand why the reactivity is very high in these kind of systems. So we can deduce various possible resonance structures and various positions where the double bond can exist in phenanthrene molecule using these various resonance structures. So if you look at all these things, we have 6 and 6 pi electrons in 2 different rings. We have structure 1, we have another structure 2, we have another structure 3. So that means out of 5 structures, 3 structures are having 2 aromatic rings having 6 pi electrons and 1 aromatic ring having just 2 pi electrons. The other 2 structures have 6 pi electrons in only 1 ring, and 2 other rings are having 4 pi electrons each. So this we can put at number 4 and this as number 5. or the two structures where only one of the ring is having 6 pi electrons and the other two rings are having only 4 pi electrons each. Let us look at how to draw various resonance structures for naphthalene, phenanthrene and anthracene. We will start with naphthalene. So naphthalene has two benzene rings attached together. So we will without the double bond, we will just draw the skeletal structure of naphthalene. Various resonance structures we will draw. There are three resonance structures are possible. Let us draw the three skeletal structures without the double bond, and then we will take add the double bonds later on. So we have three structures possible for naphthalene as resonance structures. How to draw the double bonds? So the simplest thing is start from the vertical bond. First draw one vertical double bond, and based on that we can actually fill the rest of the molecule. So we will start from the ring number 1 here in the first one. So the second double bond will come here, the third double bond will come here. So this ring now becomes fully aromatic. So the rest of the two double bonds we have to draw in the next ring. So we have two double bonds here in this particular one. And if we start from the second ring, the first vertical double bond we have to draw here, then we draw here the second double bond, the third double bond here. So with that we complete the 6 pi electrons, that means 3 double bonds on this particular ring. So we move to the next ring and complete the rest of the double bonds. So we can draw the next resonance structure of naphthalene. And for the third one, instead of the left one, we are going to start from the central one. So this is the double bond we have to draw. Then you can make this ring completely aromatic by drawing the other two double bonds. So we have 3 double bonds in this particular ring. So the remaining 2 double bonds can be drawn here. So this is the third resonance structure. So with that we can actually draw the various resonance structures of naphthalene without any difficulty. And if we want to move on to the next one, which is anthracene. Anthracene is having only one more additional benzene ring similar to naphthalene. So we can start for naphthalene. Let us have the same basic structure like naphthalene for anthracene. We have to add only one more benzene ring on to this molecule. So we draw without the double bond the skeletal structure. We can also draw additional structures compared to naphthalene. So there are 3 rings are there, so we can actually write 4 resonance structures. Let us see what are all the 4 possible resonance structures. So like naphthalene, this is anthracene. So we will start with the first double bond and then we can fill it up continuously. So this is conjugation, means we have alternate single bond double bond nature. So with that we can draw the first resonance structures for anthracene. So here we started with this ring as the vertical double bond. Then we can also start from the other end. So let us start from the other end and then complete the other double bonds here. So we have the second resonance structures for anthracene drawn. Then we can start from the any one of the internal ring. So here let us start from this side, and when I start, let us fill the double bonds in this particular ring. So we drew 3 double bonds here. Then the rest of the things we have to just add here and here. Similarly we have to draw like this in the other ring. So we can complete the third resonance structures. And in this one we started off with the double bond on this left hand side. So now let me start from the right hand side one. So we draw the double bond here. Then let us complete the double bonds of this one here. So we can easily draw all the 4 anthracenes resonance structures can be easily drawn here. So there were, if there is additional resonance structures we have to draw, then accordingly we will have to make it. So in these structures, if you look at the third ring is having a double bond at this particular end in one of the resonance structures. So we can also draw the same with the double bond here, which is seen here in this particular structure. So this double bond can be even considered for the other ring, that is the outer ring. So when we draw the Fries or the Clark structure, then the double bond only can be considered for only one of the ring and not for both the rings. So that way we can also draw the various resonance structures for anthracene. And when we move to the phenanthrene, let us draw the structure without the double bonds first. So we can draw at least a few of the skeletal structures without the double bond first. For simplicity, I will just draw two double bonds. So in the naphthalene and anthracene, we have drawn the vertical double bond first. Here we will draw the horizontal double bond first. So let us draw the horizontal double bond in the central one and make this ring fully aromatic. So then the rest of the double bonds we have to draw for this ring, and here also we can draw the rest of the double bond for this ring. So with that we can actually complete the complete structure of phenanthrene. So we started with the horizontal double bond in the first one. Now let us move to any one of the ring. So maybe let us start from the double bond in this position. Okay, first we complete this ring as all the three double bonds are written, and now leave this double bond and single bond. We can draw the double bond here, and now the second double bond for this ring will come here. Now we can complete the rest of the molecule very easily. So with that we can draw all the possible resonance structures for phenanthrene also. So if we look at the Clark and Fries structures, so the Clark structure is drawn when there are 6 pi electrons are separated by at least one ring not having 6 pi electrons. So that is how we say these are Clark structures. We can draw various Clark structures for phenanthrene, but this is considered as the most stable structure according to Clark rule. That means in this particular ring we have two 6 pi electron systems, which is much more stable compared to other two Fries structures, because this is also a Fries structures. Here we have 6 pi electron in only one of the ring, that is one of the terminal ring, and another one, the middle ring, is having 6 pi electrons. So these are all the other two Clark structures which are possible for phenanthrene, and out of that the first structure, which is having two 6 pi electron rings, are the most preferred Clark structure. And if we extend the same for Fries structure also, we can do the same thing for Fries structure also. In the Fries structure we have two benzene rings having 6 pi electrons each, and other Fries structures include one 6 pi electrons ring is present either at the one of the terminal end or at the middle. So this is how we can actually identify what are all the different probable Clark structures and what contributes more to the stability of this compound we can actually deduce. Let us continue our phenanthrene structural elucidation by preparation of phenanthrene from various derivatives. So as we have seen, phenanthrene is having three ring structures, and these three ring structures are connected through the angular fashion, and by running various cyclization reactions we can actually deduce how phenanthrene can be formed. So one of the reaction is we take a bibenzyl. So in the bibenzyl there is two carbon atoms attached or connected between two benzene rings. So this is how we can actually draw the bibenzyl structure. And when we pass this bibenzyl over a red hot tube, so basically the red hot tube is the reaction conditions under which the bibenzyl undergoes cyclization to give phenanthrene as shown here. And we can also start from Z-stilbene or cis isomer. The cis isomer of stilbene also undergoes cyclization, because what happens is these two carbons are actually connected and the bond is formed here, that leads to the phenanthrene compound as shown here. And we can also start from 2,2' dimethyl diphenyl. So from this structure we can also say two rings are already there in the starting material. 1, 2 rings are there. The third ring is formed from two carbon atoms which are attached in the ortho position. So by that we can also conclude that this is an angular fashion, or the angular fusion leads to the final product. So this 2,2' dimethyl diphenyl, when treated with sulfur or a red hot tube, in both the condition the cyclodehydrogenation leads to the final product, that is the phenanthrene is formed. So there are other methods. Here we will look at starting from benzyl. So in the previous one we had seen there is no carbonyl unit here as shown here. We have two carbonyl units in the starting material. But if you look at the previous one, in the bibenzyl we do not have any carbonyl unit. So having the two carbonyl unit leads to the similar type of cyclization. So here again we are heating or treating this benzyl with AlCl3 at 120 degrees centigrade and heating, that results a quinone derivative. So phenanthroquinone is formed, and this phenanthroquinone on treatment with the zinc dust loses this carbonyl unit to give the phenanthrene moiety. And also we can also do another type of reaction, which is a phytic reaction. So in this phytic reaction, orthobromobenzyl bromide, we have the bromo compound and this is the benzyl bromide unit. So these two are connected, or what we do is basically a intramolecular cyclization we are carrying it out. That leads to the formation of the phenanthrene derivative. Of course, this reaction also leads to the formation of anthracene. Anthracene is basically connected in a linear fashion. So this is how we can actually deduce the structure that phenanthrene is having the angular structure. So these are various ways by which we can actually prepare phenanthrene. We also have other method called SAR method. So in this SAR method, it is a multi-step reaction. The main reaction is basically the Perkin reaction. So in the Perkin reaction, we are using in the presence of sodium phenyl acetate. So basically we will generate an anion here, and this anion will go and attack the corresponding aldehyde unit, because this is a electrophilic carbon unit, and this is a nucleophilic site, and this nucleophilic site attacks the electrophilic carbon, leading to the formation of the hydroxide derivative. And under the reaction condition, that very readily loses water, because there is an extension of conjugation which is possible by the loss of water molecule. That leads to the substituted cinnamic acid derivative. So this is the cinnamic acid derivative. If there is no substituent on this particular carbon, this is a normal cinnamic acid, we have a substituent on this particular carbon, and also the aromatic ring is having the nitro group. So we have two substitutions on this particular cinnamic acid. So this substituted cinnamic acid is formed by the Perkin reaction of nitrobenzaldehyde, that means orthonitrobenzaldehyde and sodium phenyl acetate in the presence of acetic anhydride. So once this substituted cinnamic acid derivative is formed, this nitro group is reduced, followed by treatment with nitrous acid. It leads to the formation of diazonium group. That means introduction of the diazonium group is carried out by the reduction of the nitro group to the amino group. So the nitro reduction leads to amino formation, and this amino group is converted with the HNO2, that is sodium nitrite, to give the corresponding diazonium salt, and this corresponding cinnamic acid having the diazonium salt is treated with copper and sulfuric acid. So this leads to the cyclization, that means basically the condensation happens between these two carbon atoms. So when the condensation takes place, we end up with the cyclized product, and this carboxylic acid can be decarboxylated on heating, leads to the final phenanthrene. So this is how we can also prepare phenanthrene using SAR method. So of course various substituted phenanthrene can be prepared using this SAR method, because we know the starting material here what we are using is basically the unsubstituted phenyl acetate. So if we have any substituent on this phenyl acetate, we will actually end up with various substituted phenanthrene derivatives. Of course, along with the orthonitrophenylbenzaldehyde, we can also have some substituents on this particular ring also. So we can have both the rings can have different type of substituents, and based on different types of substituents we can actually get different types of substituted phenanthrenes. And one thing what we have to remember is this reaction occurs only under the cis orientation. That means when the cinnamic acid is formed, only the cis cinnamic acid can be converted to phenanthrene derivative. If we isolate trans isomer and if we try to cyclize the trans isomer, that is not going to give phenanthrene derivative. So this is a confirmation that our structure of phenanthrene is a angular ring fusion. So this can be confirmed by the formation of phenanthrene from the corresponding cinnamic acid derivative. Only the cis isomer gives the final product, that is the cyclase product, and the trans isomer does not lead to phenanthrene. Clearly tells that the ring fusion is a angular ring fusion. And when we do the reaction under copper catalyst, the reaction occurs using a radical mechanism, and if we are carrying out the diazonium cyclization in the absence of a copper catalyst, that may undergo ionic mechanism where aryl cation is the intermediate that is involved in the cyclization reaction. So that is very similar to electrophilic aromatic substitution reaction. And this reaction is also an example of intramolecular phenylation reaction. That means intramolecularly, that is within the molecule, the phenylation, that means attachment of one phenyl unit to the other aromatic system happens. And the next method is the Haworth method. So in this Haworth method, we are starting from naphthalene derivative. When naphthalene is treated with the succinic anhydride in the presence of AlCl3, so this reaction is nothing but a Friedel-Crafts reaction. So the acylation actually takes place, leading to the formation of a keto acid, and this keto group can be reduced by zinc amalgam in the presence of HCl. So this carbonyl undergoes reduction to give the corresponding carboxylic acid, and the cyclization of this carboxylic acid using sulfuric acid leads to the keto derivative. And again, once again, this particular keto group can be reduced using zinc amalgam, leads to the cyclized product without the carbonyl unit. And finally, the dehydrogenation of this alicyclic system using selenium gives the final phenanthrene derivative. So this also additional information to confirm that phenanthrene is having 3 ring units, because here we are starting from 2 naphthalene, that means naphthalene having 2 benzene rings, and we are adding one more alicyclic system into this compound. So 1 plus 2, and the third one comes from this particular moiety. So we can say the phenanthrene is having 3 benzene ring structures. So there is also some modification to the Haworth method. So using similar to the SAR method, here the Haworth method can also be used to prepare various substituted phenanthrene derivative compounds. Say for example, if we are starting from the succinic acid having substituent, or here we can see the succinic acid is having the substituent. So when we have the succinic acid having the substituent, our final product, that is the phenanthrene, is also having a substituent. So like that we can actually get a different substituted phenanthrene starting from any of the molecules having the substitution. If you have some substitutions on the naphthalene ring, that also leads to various substituted phenanthrene derivatives. So, having a substitution on succinic anhydride or on the naphthalene leads to various substituted phenanthrene derivatives. And we can also carry out a Grignard reaction on the corresponding keto compound. But if you do a Grignard reaction on this particular carbonyl compound with any of the methyl magnesium bromide or other alkyl magnesium halides, then we end up with a corresponding substituent on this position. So, that leads to substituted phenanthrene derivatives. So, the phenanthrene derivatives can be prepared using Haworth method, either starting from an entirely different starting material, or maybe the one of the group, that is the substituent, can be introduced in the in between steps, that is the carbonyl derivative or the keto derivative. So, there is another method by which we can prepare phenanthrene. So, here 1-methyl phenanthrene can be prepared from 2-acetyl naphthalene. So, here we have the acetyl group which is in the 2 position of the naphthalene moiety. This is basically nothing but a Stobbe condensation reaction. So, we have a carbonyl unit, we have an active methylene compound. So, this is the active methylene compound which can be generated an anion with the treatment with the base. So, here we are using sodium tertiary butoxide as the base to abstract a proton from this active methylene carbon. That leads to the formation of anion, and this anion actually attacks the electrophilic carbon, and then this oxygen gets the negative charge, and finally that on charge reversal we end up with this cyclic lactone derivative. And this cyclic lactone derivative can be hydrolyzed to open up this particular ring. We end up with the corresponding carboxylic acid, and this carboxylic acid can be further converted to or cyclized using hydrogen fluoride to give this corresponding keto derivative, and we end up with the substituted phenanthrene derivative on pelletized carbon reduction of this particular alicyclic ring. So, this is also another method to give the corresponding or the substituted phenanthrene derivatives. So, if you look at the reactivity of phenanthrene, as we have seen earlier, there are 2 Clar structures which are more stable for the phenanthrene moiety. So, in this particular case, we have 2, there is a double bond which is fixed or maybe present in 4/5 of the structures, because earlier we have seen various structures, and in most of the structures this position 9 and 10 always has a double bond. So, this double bond actually behaves like a normal double bond and not a benzene like a double bond. So, this particular double bond undergoes addition reactions very readily. So, we always end up with the hydrogen or halogen addition takes place between this position 9 and the 10 position, are highly reactive whether we follow the Clar structure or we follow the Frey structures. In both the structures, this 9 and the 10 position always has a double bond. In other words, this behaves like an isolated double bond, and the reaction very readily takes place at this position. Because as you know, reactivity and stability are inversely related. So, whenever there is a stable structure, that is 6 pi electron structures, this ring is going to be highly stable. So, this does not undergo addition reaction very readily. Similarly, this ring also has a 6 pi electron structure, so which is also quite stable. So, this also does not undergo reaction very readily. But on the other hand, the middle ring is having only 2 pi electrons. So, this is an isolated, this behaves as if like it is an isolated double bond, and the reaction very readily takes place at this position. So, we have various examples of phenanthrene's reactivity. We can look at bromination reaction. So, when we do the bromination in the presence of iron, we end up with a 9 substituted product. And this bromo derivative on treatment with cuprous cyanide gives the corresponding cyano derivative, and the cyano derivative can be hydrolyzed to give the corresponding acid. So, we can actually form the corresponding carboxylic acid, that is 9 carboxylic acid, 9 phenanthrene carboxylic acid can be prepared starting from the phenanthrene using bromination, cyanation followed by hydrolysis. And when we do the chloromethylation, the reaction occurs at 3 positions. Nitration also gives various derivatives, like 3 mononitro derivatives are formed, where substitution at 3 position is a major product, because these are electrophilic substitution reactions. In this particular case, the aromatic ring undergoes the reaction and not the isolated double bond. So that is the difference. So when we do simple addition reactions, the double bond undergoes reaction very readily. Whereas when we use iron, and again the iron position undergoes reaction very readily. Chloromethylation and nitration, which are very typical examples of electrophilic aromatic substitution reaction, happens on the aromatic ring. So that means instead of 9 and 10 positions, 3 position undergoes the reaction very readily. And when we do sulfonation reaction, here again 1, 2, 3 are the major places where the reaction actually proceeds. And of course some amount of 9 substitution is also formed in that reaction. So with that, what we can understand is, whenever we carry out electrophilic aromatic substitution reaction, that occurs in the aromatic ring. And when we do simple addition reaction, that occurs in the double bond, isolated double bond position. So if we look at the structure, we can draw the structure of phenanthrene. So these two positions are basically 9 and 10 positions. And when we start from here, numbering 1, 2, 3, 4, 5, 6, 7, 8. So we can draw the double bonds accordingly. So this 3 position, if we look at these two rings are basically the aromatic rings, which are having benzene like structure most of the time in the Fries and Clark structures. So these rings undergo aromatic electrophilic substitution very readily. So that's the reason nitration, sulfonation, all these reactions occur at position number 3 in the benzene ring. And if you look at the ozonolysis reaction, the ozonolysis actually undergoes at the 9-10 position, because this is an isolated double bond, and the ozonolysis or the ozonide formation very readily occurs on this double bond. Hydrolysis of this ozonide actually leads to the dialdehyde derivative, and this on KMnO4 oxidation directly leads to the corresponding dicarboxylic acid. So this is nothing but the diphenic acid, and this also clearly tells, like these two positions are actually connected through a double bond, which also further gives evidence to the angular structure of phenanthrene. And oxidation, as we have seen, as one of the crucial reaction for structural elucidation, when the reaction is carried out with sodium dichromate or chromic acid in the presence of acetic acid, leads to phenanthroquinone as shown here. And this phenanthroquinone on treatment with the warm alkali actually undergoes benzylic acid rearrangement, and we end up with the corresponding hydroxycarboxylic acid. This on the loss of carbon dioxide gives the corresponding hydroxide derivative, which is called fluorinol. On oxidation, this leads to fluorinone. So here we actually lose 1 carbon unit from the starting material. So this is how a 6-membered ring can be converted into a 5-membered ring. So this is what is the ring contraction reactions of phenanthrene. Let us recap in the summary what we have studied so far. We have studied about the structural elucidation of phenanthrene. So what is the molecular formula of phenanthrene, and how many rings are present in phenanthrene, whether they are connected through angular fashion or linear fashion, all those things we have studied. We have also studied about the position of various double bond, how many resonance structures are possible, how many Fries structures and Clark structures are possible for phenanthrene we have studied. Based on that, we also deduced what is going to be the highly reactive site for phenanthrene. We also concluded the structural elucidation with the preparation of phenanthrene from various derivatives. We studied about Wittig-Fittig reaction. We also studied about Sauer synthesis, what is Haworth method, and how Friedel-Crafts reaction can also be employed in the preparation of phenanthrene we have seen. What is Stobbe condensation, that also we have studied. So these are all the various methods by which how phenanthrene can be prepared we have studied. We also studied about the various reactions of phenanthrene, like a reduction reaction, halogenation reaction, oxidation reaction. What are the different products that are possible from phenanthrene? All those things we have studied. With that, we conclude this session. Thank you.